This is section 5.1, angles and their measure. And we will be wanting to find degree measure first. And in order to do that, we will need to talk about an angle, its initial and terminal side, and of course the vertex. So looking here to the right, you can see we have the vertex right here. And then we have the initial side, which is the starting position. And we rotate from that initial side to the terminal side. Now, an angle is in standard position if its vertex is at the origin in the XY plane. Okay, so as you can see, if we have a vertex here, then we have an angle in standard position. And you can see over here to the left that the initial side is positive x-axis, and here the vertex is at the origin. And that is an angle in standard position. Now, the measure of an angle can be positive or negative. And if the angle rotates counterclockwise, then the measure of the angle is positive. And if the rotation is clockwise, as you can see here, we're going to have a negative angle. And you can see this angle, whoops, this angle is negative 150. Because we rotated counterclockwise here, our angle is positive. And a degree is one way to measure an angle. Now, for a full rotation of a ray about its endpoint, we would have to rotate 360 degrees. That is a full rotation. And now you could think of 1 degree is 1/360th of a full rotation. Let's go ahead and just take our time and begin by sketching angles in standard position. We will actually sketch both of these. As you can see, 120 degrees. So we're going to begin in standard position, and we're going to rotate 120 degrees. Now, if this entire plane is 360, then 360 divided by 4, so this would be 90 degrees. Now, we need another 30 degrees, so we will actually continue on to here. And we could just go ahead and draw that, and we would write 120 degrees. And what do you notice? We notice that we are in quadrant 2 once we have this measure of this positive angle, and we rotate 120 degrees counterclockwise. We're in quadrant 2. Now we have negative 70 degrees, so we will be rotating clockwise. Again, this is 90 degrees, so we're not going to go quite to 90. So we'll go just before 90, maybe about right there, and then we will write negative 70 degrees. And what do you notice? We are in quadrant 4. Okay, now we're going to have some very special angles, and because they're so special, they have names. So we'll look at a right angle, and that measures 90 degrees, and as you can see, that's 1/4 turn. Then we'll have a straight angle, and as you can see, we rotate 1/2 of a turn, and we have gone counterclockwise from here to here. And then acute. An acute angle is an angle that is less than 90 degrees, and an obtuse angle is greater than 90 degrees, and we say 90 to 180. So as you can see, both of these angles below, note acute and obtuse. Remember, this is 90 degrees, so that is why this angle is acute, because it is less. And since this is 90 degrees and we rotated more than 90, that's why we have an obtuse angle. Okay, we also have some special angle names of complementary angles and supplementary, and this deals with two angles. So these are all names for single angles. And these are properties with two angles. These are two angle properties. Okay, and so if you have complementary angles, if you add up the measures of the angles, they will equal 90. So what would you say that the complement of a 30-degree angle would be? That's correct, 60 degrees. Why is that? Because 30 plus 60 equals 90. So these are complementary angles. How about supplementary? This is when the sum of the two angles is 180 degrees. So the supplement of 130-degree angle must be a 50-degree angle. That's correct, and that is because 130 plus 50 is 180. Okay, now let's get a little more detailed about degrees. A degree can be divided into 60 equal parts, and these are called minutes. That's kind of easy to remember. And then each minute is divided into 60 equal parts, called seconds. So we have 60 seconds in a minute, and we have 60 minutes in a degree. And you can see those right here. So let's do some converting. Let's convert to decimal degrees. So we're given 38 degrees and 12 minutes. So how would we convert that? Well, let's start with 38 degrees, and we have 12 minutes added to that. Now we're going to have to convert minutes to degrees. So as you can see here, we have 1 degree is equal to 60 minutes right here. So, So we will have, and I don't have to put that parenthesis there, I can just put it times 1 degree is 60 minutes. Now these minutes will cancel, and we're just left with degrees. So we know that we're doing pretty good there with our units, okay? So 12 divided by 60 is 1/5. So 12 divided by 60 is 1/5. So we will cancel these out and put 1/5. Okay? So now what do we have? This is equal to 38 degrees plus, and what is 1/5? And I can go ahead and write that here. 1/5 of a degree, and 1/5 is 0.2. So we have 38 degrees plus 0.2 degrees. See if I can make this a tad bit smaller. I made that awful large. And now we have, move this over. And now we have 38.2 degrees. Now let's go the other way. Let's convert to degrees, minutes, and seconds. And we will begin with 120.45 degrees. Now, let's convert this 0.45 degrees, and we will have 120 plus 0.45 degrees, and we will multiply that by 60 minutes divided by 1 degree. So there are 60 minutes in 1 degree. So now we have 0.45 times 60. You can do that in your calculator if you want. So we have 120 plus 0.45 times 60 comes out to be 27. And again, these degrees will cancel and we just have minutes left. So now we have 120 degrees and 27 minutes. Okay, so both of these conversions depended on what? 1 degree equals 60 minutes. That was very handy for those two examples. Now we're going to move on to radian measures. And radian measures are different than degree measures. And you're going to have to know the difference. And when you're using your calculator, you will have to use either radian mode or degree mode. So now let's go ahead and take a look at what we have. When two lines or rays cross a circle, the part of the circle between the intersection points is called the intercepted arc, and it's often denoted by S, and you can see that S right here. A central angle is an angle with the vertex at the center of the circle. So you can see the central angle there shown. So a central angle that intercepts an arc on the circle with length equal to the radius of the circle has a measure of 1 radian. Now that may seem like a lot, but I think as we work through these examples, you will see that radians tend to be quite easy to work with. So 1 radian can be written as 1. We have no units on radians. They say it is unitless. Okay, so now let's talk about a radian measure of an angle. The radian measure of a central angle theta subtended by an arc of length S. So the arc length is S and the central angle is theta. We can now write that theta equals S over R. And so that is the radian measure of an angle. Now, the number of radians in 1 revolution, if we would write S over R, this would be the entire circumference of a circle, which you know already is 2 pi r, divided by the radius. And what happens to those r's? They cancel. And you're just left with 2 pi. And 2 pi is about 6.28. So the measure of 1 full revolution in degrees is 360 degrees. So what do we know now? We know that 2 pi equals 360 degrees. If you'd like to divide both of those by 2, then you will have pi equals 180 degrees. Either way. Okay, so how are we going to convert between degree and radians? Just with what we have here. You can use pi over 180 degrees if you want to convert degree to radians, or if you want to convert from radians degrees, starting with radians, you'll multiply by 180 degrees over pi. Make sure you're using your units. It makes everything a whole lot easier. Let's begin with converting from degrees to radians. As you can see, we're starting with degrees, and we want to end up with unitless radians, okay? So how are we going to do that? We'll begin with 120 degrees. So we want degrees in the denominator to cancel that. And as we said, there are 180 degrees in pi radians. And if we take 120 and divide it by 180, you will see that you will get 2/3. Let me show you that in the calculator. I tend to let students follow along in the video with their calculator and pause, but I just want to make sure you know that if you have 120 divided by 180, you can press this math button and then press frac number 1 and press enter, and it will give you the fraction, which is 2/3. So I will assume you will be working on your calculator alongside and checking those reductions when I give them to you. So now what do we have left? We have a 2 and a pi left. I didn't write that very neat. So we have a 2 and a pi left divided by 3. Okay. So now, well, that didn't do a very good job there. Okay, so now how about negative 300 degrees? We're going to use that same factor, pi divided by 180 degrees, because we want these degrees to cancel so that we're left with radians. So now when we divide 300 by 180, you can try that in your calculator, or negative 300 divided by 180, you will be left with a negative 5/3. And so now we have negative 5 pi/3 radians. Now let's go the other way. We're going to convert from radians to degree, and we will just reciprocate what we just used. So now we're going to multiply this by 180 degrees equals pi, or that same factor. So as you can see here, the pi's, the pi's are going to cancel, and we'll have 180 divided by 9. So 180 divided by 9, that will be 20/1. So we can't forget about that 8 in that numerator, as you can see. So we end up with 8 times 20, which is 160 degrees. Okay. So now let's try one more of those, negative 1.8. So we'll multiply again by 180 degrees over pi. And now, as you can see, we will just multiply right across, and we will end up with a negative 1.8 times 180 is a negative 324 degrees over pi. Now, if you put that in your calculator, I'll show you how to do that. So if we go ahead and put a negative 324, and we divide that, and as you can see, pi is above this arrow, but we need to have second arrow up. And there we will get an approximation. I don't know why that did that. Let me try that. The opposite of 324 divided by pi, and we'd get negative, I think I used a minus sign, a negative 103.132. Let's just go to 2 decimal places. So that was 103.13. So negative 103.13 5.13 degrees. Okay, now let's talk about coterminal angles. Okay, and coterminal angles are two angles in standard position with the same initial side and the same terminal side. So let's take a look. These angles in standard position are coterminal if their measures differ by a multiple of 360 degrees or a multiple of 2 pi. So in other words, we will just be looking to see if they had an additional rotation. So taking a look at this first example, if we have theta equal to 50 degrees and theta equal to 410 degrees, and we add those together, we will get, if we add 360 degrees to 50, we will arrive at 410 degrees. And as you can see, we rotated 50, and then we rotated another 360 and ended up at 410. And I'll show you that. So this is 50 degrees. We rotated 360 degrees and we ended up back here again. So we have coterminal angles. These are coterminal angles because their degree measures differ by 360 degrees, okay? Now let's look at this next example. Theta equals pi over 6 and theta equals negative 11 pi over 6. And as you can see, if we subtract 2 pi, remember we can add or subtract. It's a multiple. We come up with negative 11 pi over 6. So, and doing that subtraction, you can do that by hand, or let me just show you this real quick. Pi over 6 minus 2 pi is the same as 1/6 pi minus 2 pi. And if on your calculator you take 1/6 and subtract 2, I'll go ahead and show that to you just in case. So we have 1/6 minus 2 math frac will have a negative 11/6. So we have a negative 11/6 pi, and that's the same as this, a negative 11 pi over 6. Okay, so now let's just try a couple examples. We're going to be looking for a positive angle and a negative angle that is coterminal to the given angle. So we're looking for a coterminal angle, okay? Coterminal angles are the angles that differ by these multiples of 300 degrees or 2 pi radians. So how are we going to do that? Well, since we're given degrees, we could take 110 degrees and add 360 degrees, and we'll come up with 470 degrees. Now, if we have 110 degrees and we subtract 360 degrees, we'll have negative 250 degrees. So 110 and negative 250 are coterminal angles, and 110 and 470 are what we call coterminal angles. Okay, now we're given radians here, so we're going to have negative pi over 4 plus 2 pi and negative pi over 4 minus 2 pi. We're going to do the same thing we did last time. We have a negative 1/4 pi plus 2 pi, and we have a negative 1/4 pi minus 2 pi, And if we do those in our calculator, if you have negative 1/4 plus 2, you will have 7 pi over 4, or 7/4 pi. And again, we will have a negative 9/4, whoops, fourths pi. And we really need to put that pi in the numerator. I kind of split that out in order to solve those, but we could put it like that, okay? Okay, how about number 7? Find an angle between 0 and 360 that is coterminal to this angle 910. Now, keep in mind, we have to continue to find the difference of 360 degrees until we get an angle between 0 and 360. So let's just start subtracting. We have 910 minus 360. And we come up with 550 degrees. Let's do it again because 550 is not between 0 and 360. Let's subtract again, and we get 190 degrees. And there we have it. So what would we also say? We could say 910 degrees minus 2 times 360 degrees is equal to 190 degrees. Okay, I guess I could have put that right there. Okay, let's try negative 80 degrees. Let's start adding 360 degrees to this angle. So plus 360 degrees, and because we need to find an angle between 0 and 360. So we're going to have to go for it. We're going to have to move in a positive degrees, 360 positive degrees. So if you add this together, you come up with 280 degrees. So that makes it really nice. Let's go to radians. Find an angle between 0 and 2 pi that is coterminal to the given angle. So here we go. We need to find an angle between 0 and 2 pi, and we're already at 17 pi over 6. So we're going to have to subtract 2 pi and see what we get. So again, if on the calculator, whoops, if you want to take 17 divided by 6 minus 2, we come up with 5/6. So we will have 5/6 pi. Okay? Now, let's try B. We need to, and 5/6 is between 0 and 2 pi. Okay? 5/6 is just under 1. So that's just under pi. Okay, going to B, negative 35 pi over 12. We need to try to find an angle between 0 and 2 pi. So we're going to have to start adding 2 pi, and let's see what we get. Negative 35 divided by 12, and we're going to add 2. Let's math frac that, and we have a negative 11 pi over 12. So we have a negative angle, and we must find one between 0 and 2 pi. So we are going to have to do that again, and we're going to have to now find a negative 11 pi over 12, and let's add another 2 pi, and so see what we get. Let's add 2 to that, and now, oops, I might have done that incorrectly. Let me clear that. So negative 11 divided by 12 plus 2. And we get 13 over 12. And we are between 0 and 2 pi if we are at 13 pi over 12. Okay, now let's end our lesson. Of course, we'll have, actually we're not ending with this arc length. We will talk about linear and angular speed after this. This is quite a big section and a lot to learn in one section. Okay, so now let's talk about the arc length of a sector of a circle. So if we're looking for the arc length and we're given a circle of radius r, the length of this arc length right here is r times theta. So it's this radius times theta. That is the length of this arc. So let's try one. Find the exact length of the arc. So here we're finding the length of an arc intercepted by a central angle theta on a circle of radius r. And we'll round to the nearest tenth of a unit. Okay? So they give us theta and they give us r. So we might as well find the arc length is r theta, and that would be 14 times pi over 12. And if you take 14 and divide it by 12, you will have 7 over 6. And we end up with 7 pi over 6 meters. Okay, since this is meters. Now let's try B. We're given angle. We're giving angle measure in degrees and r, but we still use the same formula. So the arc length is r theta, and that's going to be 2 times 20 degrees. And I really should put feet in there, but I try to just wait on my units until I'm finished. 2 times 20. Well, actually, we need this in radians. Sorry about that. Because we have to have theta in radians only. Okay, so let's go over here to the side of our paper. And if we have theta, move this, theta is equal to 20 degrees. And remember, we're going to have pi divided by 180 degrees. And that's equal to pi over 9 radians, okay? So those degrees canceled, remember? And then 20 over 180 is 1/9. Okay? I'll try not to write over those a lot so you can still see that. But anyway, so now we have 2 times pi over 9, and we have 2 pi over 9 feet. Okay? So this is 2 feet. Radians are unitless, so that's why we have feet. Over here in part A, we have pi over 12. Theta is pi over 12 radians, but we have 14 meters, and that's why we end up with meters. Okay, taking a look at number 10. Key West, Florida is located at 24.1 degrees north, 81.8 degrees west, and Cleveland, Ohio is located at 41.5 degrees north and 81.7 degrees west. Since the longitudes are nearly the same, the cities are roughly due north and south of each other. Using the difference in the latitude, approximate the distance between the cities, assuming that the radius of the Earth is 3960 miles. Okay, so how are we going to look at this? Let's go ahead and write Key West down. And that's 24.1 degrees north. And we have 81.8 degrees west. And then we have Cleveland is 41.5 degrees north and 81.7 degrees west. They are saying that these are nearly the same. So they would just like for us to look at these latitudes. Okay, so what are we going to do? Let's go ahead and subtract them. So we have 41.5 degrees minus 24.1 degrees, and we'll have 17.4 degrees. Now, we need theta in radians. Okay, so we have theta equal to 17.4 degrees, and you guessed it, we're going to have pi divided by 180 degrees. Again, those degrees will cancel, and if you put that in your calculator, you'll have 0.3, and that's radians. We won't write those units, but I will put that in parentheses. So now what can we do? We can say that, and they asked us to find the distance between the cities, which is going to be that arc length, and that's r times theta, and that's equal to 3960 miles. And remember, theta is in radians with no units, and we have 1188 miles. So that was kind of a cool problem, and you'll have lots of practice with those, and I think that makes sense. Okay, let's now look at linear and angular speed. So in order to compute linear and angular speed, we need to find out what these definitions are. And they're quite simple, especially after you have used them. So angular speed and linear speed are a little bit different. So angular speed uses this symbol, and linear speed will use this symbol. Whoops. V. Okay, so W and V. But so what will we have? We will give those a try. So angular is theta divided by t, which is the time, and linear speed is this arc length divided by the time. And of course, we know that S equals R times theta, and that's why we have this. Now, what do you notice? Do you notice that if we have theta over t is the angular speed, theta over t right here is the angular speed. So that is where we come up with r times the angular speed for linear speed. So it depends on what you're getting. So let's look at number 11. A wheel with a diameter of 1 foot spins at a rate of 40 revolutions per minute. What is the angular speed? So let's go ahead and look at our angular speed. We have W equals theta over t. And again, theta is, that W is given as 40, and we have revolutions in 1 minute. So they really gave us that angular speed. They gave that to us, but now we are going to convert that 2 radians, okay? So how do we do that? We have 2 pi radians in 1 revolution. And so when we work that out, we come up with 80 pi radians per minute. Or, since radians are unitless, we have 80 pi per minute. Okay, let's look at B. How fast in feet per minute does a point on the edge of the wheel spin? So now we are looking for linear speed, okay? So if we're on the edge of the wheel, that would be our linear speed, okay? So we have V equals R times W, since we have W here. So that radius we would use, if the diameter is 1, if the diameter is 1 foot, that means the radius is 0.5 feet, or you could put a half, okay? So we will have 0.5 feet. We'll use our W, which is 80 pi per minute. And working this out, we come up with 80 times 0.5, or 80 times a half, is 40 pi feet per minute. And if you'd like, you can take 40 and multiply it by pi in your calculator, and you will get about 126 feet per minute. Okay, last thing is we're going to be looking at the area of a sector of a circle. And it is quite simple to look at the entire area of a circle and then just find the area of this sector. Now, how would we do that? We will use theta, which is this theta. We will use the radius, which is this radius, and we will square it, and then we will multiply by a half. Okay, so let's try one of these. A circle has a radius of 12 feet. So let's go ahead and just write that is 12 there. And actually, if that is 12, this is also 12. Those are the radii. And we have 135 degrees. So we passed up 90 and we're going there, and we have 135 degrees. Okay. And now, I guess I didn't need this arrow there. Just go ahead and put 135 degrees. So now they've asked us to find the area of that sector. So we're going to use this equation. So area is 1/2, and now we need R squared, and so that would be 12 feet squared. But now we need theta in radians, okay? So working on that over here, if we have theta equals 135 degrees, remember we have pi over 180 degrees. We're multiplying it by, because 1 pi is equal to 180 degrees. And you can reduce that. This comes out to 3 over 4. And we end up with 3 pi over 4. So that's what we're going to put right over here. 3 pi over 4. Now, we have to be careful because we're going to have a 1/2, a 12, and a 3/4. Okay? And that 12 has to be squared. So why don't I write that out? We have 1/2 times 12 squared times 3/4 times pi, and all of that is going to be theta squared. So this is what you'll be doing in your calculator. And so I hope that that helps. You might even want to write this out, times 144 times 3/4, and then we have that pi again and our units. And if you multiply all of that out, you'll come up with 54 pi theta squared. Or if you put 54 in your calculator and multiply it by pi, you will have 169.6 theta squared. And that concludes this section.